All right, we can go ahead and get started. So welcome everybody to today's webinar. This webinar is hosted by the National Weather Service Office of Science and Technology Integration. The goal of this webinar series is to enhance communication and share advancements in all aspects of the UFS, both in research and operational settings. My name is Alex Elder. I'm here to help coordinate and deliver the webinar. Feel free to contact us at OSTI if you have any comments or suggestions. Also, if you have any recommendations for speakers that you would like to present at this webinar, you can email your recommendations to ufs.modeling@noaa.gov, and we will take your suggestions into consideration. Due to the high number of attendees, you will be in listen-only mode during the event. You will not be able to unmute. If you have any questions now or during the event, please submit them via the Google document that will be provided in the chat shortly. Today, we'll be hearing from Emily Faber on improving dust emission models, wind speed, bias, and alluvial flows. Emily Faber is a PhD candidate in atmospheric physics at the University of Maryland, Baltimore County, mentored by Dr. Adriana Rocha Lima. She holds a BSc in physics from Clemson University and an MSc in atmospheric physics from UMBC. Emily's research focuses on dust emission and transportation drivers using global models and measurements. A key aspect of Emily's research investigates the impact of wind speed on dust emission. Her work compares observed wind speeds to modeled values in these areas, identifying discrepancies and understanding the seasonal variability of wind patterns. Her work with the Go-Kart dust emission scheme explores how these variations in wind speed alter dust emission rates and points to methods of improving accuracy of dust transport models. Emily's research also addresses the crucial role of mineral dust in the climate system. She examines how alluvial dust hotspots emit outsized quantities of dust. Using the Unified Forecast System, Emily explores the representation of alluvial flows, areas of dry lakes and riverbeds that, despite being subgrid to the model, significantly impact dust emission due to their efficiency in seasonal and decadal cycles. Her work has earned her accolades, including the Wings Fellowship from NOAA and the GE Star 2 Fellowship. In her free time, Emily enjoys traveling and rewatching her favorite show, Star Trek. She has been known to travel to deserts and work to mentor younger students by showing them her passion for earth science. So I'm going to go ahead and turn it over to Emily to give her presentation.
Awesome, thank you. Can everybody hear me and see me all right?
Yep, we can hear you and see you. Thank you.
Perfect. Then I'm going to go ahead and jump right into it. It's a really great introduction to who I am. But like I said, I'm Emily Faber. I am at UMBC. This is hopefully my last year of my PhD. We're trying to defend by May. And so I'm in the last mad dash here. And I am super excited about dust and dust emission schemes. And so I'm hoping you'll pick up a little bit of that excitement throughout this talk. Two of my main prongs of study are with wind speed biases in models and alluvial flows, and I'm going to talk about them both here. So let's get started. So a little bit of an outline so that nobody gets lost. I like to include just a brief background of what I mean when I say dust, because I say dust all the time, and then it's like, oh, grandma called me and said, oh, you can study all the house dust that I have, and it's really more of a mineral dust and how it interacts with our climate system. And then the main part of the talk, I'm going to do two sections. The first one is on wind and how a recent study we studied the wind speed biases and how they impact the dust mass emitted, especially in the Arabian Peninsula. And then the second one is kind of the more work in progress. And so I'm going to show some study results and also have a little bit more of a discussion about where we're going with it. And this is the alluvial flows part. And I'm going to, of course, give you some key takeaways. The picture on the right is me as right after I sprinted up a desert dune in White Sands, New Mexico last summer, I think it is now, because I was excitedly pointing at this dust devil over here. So I'm super excited about dust. If you have anything you want to talk to me about dust anytime, I'm here for it. Love it. Let's get into it. So as an introduction, like I was saying, I study mineral dust. This is just a nice, pretty picture to show you what I mean when I say large-scale desert dust. This is a sand sea in the Arabian Peninsula and an absolutely beautiful dust storm over it. This area is what's blowing. There's a wind coming up from the southwest there and taking this huge dust storm. So dust has a large role in our climate system in a couple of different places. At any given time, if you take all of the aerosols out of the air around the entire globe, you'll find a majority of it is actually mineral dust, and even down to the smaller fine modes, less than 10 microns, 35% of that could be dust in the continental aerosols. Once it gets into the atmosphere, like you see coming off of the west coast of Africa here, it impacts radiative balance of the planet. So like it'll reflect the incoming solar radiation back up to space, and it'll actually cool the area underneath it. It'll also interact with the water vapor field in those areas and do what's called first and secondary aerosol or cloud effects. And so these are interacting, the particles are interacting with the water vapor field in the area, and it can either lead to like cloud brightening or hurricane suppression, depending on how much and where it is at any given time. From a more biological background, dust is an incredible driver in our climate system. One of my favorite fun facts, again, is if we didn't have the Sahara Desert, like the plumes that you see here, we really wouldn't have the Amazon rainforest, at least not how we know it today, because there's so much bioreactivity in the dust that's carried across the entire Atlantic to the other side to fertilize these rainforests. Along the way, it's of course fertilizing more like algae blooms and such, so the ocean floor benefits from it as well. And then just from like a human standpoint, if you were standing in a dust storm and breathing, you're probably going to be very uncomfortable. There's things called like desert lung is an entire thing that you don't want to get. It can carry things like meningitis, and so this impacts like people's actual like everyday health. And then in the American Southwest, there's a large problem right now where there's large dust storms kicking up, and they're hard to predict, and they impact like large highways and interstates, and will cause like car wrecks and unfortunately like deaths. So it's a huge global impact across all kinds of different backgrounds. So the wind speed bias study. This was a recently accepted paper in JGR Atmospheres. We're very excited about it. And we looked at how wind speed biases in the MERA2 reanalysis, which is uses the go-kart dust emission scheme, impacts the dust emission and how much that changes between measurements and models. And if you want to read more about it, like I said, it's forthcoming because I've really only got time to touch on a few basics here. So let's get into it. The study basically asked if we can quantify the bias in dust mass emission due to the observed wind speed biases within the MERA2 reanalysis, and more specifically the go-kart dust emission scheme, which is used not only in the GEOS model and the reanalysis here, but it's used in the UFS as well. So what we did was we took 30 stations, and I've highlighted them on the right-hand side here in the green dots. And these are historical stations from NOAA. They're called the ISD, the Integrated Service Database is what you'll hear me call it. And these have records for decades, and they're very trustworthy, and they're quality controlled, and they're screened, and they're around the entire world. We focused on the 30 in the Arabian Peninsula, and I've also plotted on here like some of the AeroNet sites that you might know and love already, so you get a sense for where these things are. These have like standardized reporting. One of them, which is 10-meter wind speed, which is exactly what we need to be able to compare to the go-kart dust emission scheme. And probably most importantly is when we were first starting the study, we needed something that was separate from the MERA2 reanalysis. So we needed an independent data set, and the answer to that was the ISD wind speed. These are not assimilated, being a reanalysis, they are completely independent. So what did we find? We found that the wind speed disagreement between measurement and model is not uniform. And when I say not uniform, I mean it's not uniform in space. So this is the same 30 stations, and I've highlighted 4 of these for some case studies here, which I'll walk you through real quick. So this is the monthly wind speed average for all months in this study, which was 20 years. And in the orange, you've got the MERA2 reanalysis. And in the blue, it's the ISD. And in the little parentheses down here, it says time coordinated values. So this is actually really important. What we did was we found these 20 years of data at these stations, and for anything that was missing, so like a logger went down or somebody just didn't report it that day, we threw out the corresponding hour measurement from the MERA2 data set. So we're trying to compare apples to apples across 20 years here. And that's the case for all of these. So we found 4 major categories of stations and different types of agreement or disagreement here. The first one was agreement. We had a couple stations that they look fantastic, right? Like the orange follows with the blue really well, the magnitude's really well represented, the seasonality is well represented. There's no large drifting throughout the 20 years, anything like that. Beautiful station. Then on the diagonals, you see the flat seasonality and the seasonal bias stations. These are different between measurement and model for probably 2 different reasons, which I'll talk about in a minute. The seasonal bias stations don't get the mins and the maxes very well, and this particular one, the MERA2, is on the whole higher wind speed, and so this is going to lead to a overestimation of dust mass emitted later because it propagates through a cubic before you get to a flux equation in the dust emission. And then a similar problem, but different in the flat seasonality case. So you see this one doesn't get the mins and the maxes, but it also doesn't get the location in space right. It doesn't get the seasonality correct. So you might see like this might be a peak in June and a trough in January, but the MERA2 doesn't agree that that's where the peaks and the troughs are. And so these might be 2 different reasons. I'll talk about them a little bit more in a minute. The last one that we saw a lot of, and this was the MERA2 overestimation case. So a bunch of these stations did this. This one is a really pretty example because it shows almost a 2 meter per second difference on average, which is incredible when you propagate that through a mass emitted at the other end. Like it goes through a cubic, so you're gonna see a large difference there. And these wind speed disagreements being not uniform led to these differences in mass emitted, like I've told you. So this is a lot going on this slide, so I'm gonna walk you through it real quick. This is all 30 stations like we've been talking about, and their locations are over here. And then on the x-axis is a year. And so each one of these squares is the difference between the mass emitted using ISD winds and the mass emitted using MERA2 winds. So I'm gonna say it a little bit of a different way, is that we calculated the mass of dust emitted using the same physics as in the go-kart dust emission scheme using the ISD winds, and we did the same thing for the MERA2 winds, and these are time and space correlated. So, and then we subtracted the 2, and so that's what you're seeing here represented for each year. And you see interesting things like an oscillation going on between a negative and a positive difference. You see things that are just always a positive difference, red all the way through. You see blue all the way through. And then I wanted to know how this looked spatially. And so I averaged each one of these rows, and that's what the color corresponds to on the right-hand side. So this ends up being the yearly average mass difference between measurement and model for each one of these 30 station locations, and this is over the span of 20 years again. And what we noticed was that there was 2 main regimes that emerged: this upper regime, which has more red circles, and this lower regime, which has more blue circles. And so there's more of an overestimation in the top and an underestimation in the bottom. And there was a lot of discussion, and you can read more about it in the paper about why this is. Ultimately, it's kind of a mesoscale issue and a seasonal to subseasonal timing issue that we think is going on here, mostly because of something that's called the Lavar and the Shamal winds, which happens in this general area, which we think leads to this bias in the north. So like I said, those issues are because of that 10-meter wind speed parameterization, because even if you have those big mesoscale misses or the subseasonal to seasonal issues going on, you are ultimately drawing on those values and those equations to get your 10-meter wind speed. And we were able to show that using a KZ filter. So on this top left-hand plot is all of our measurements and all of our model values. All of our apples to apples are plotted on top of each other, so it looks a mess. But you can already see that the MERA2 in orange doesn't get all of the peaks that the ISD sees. And these are like the gust speeds or the localized wind discrepancies that are not being picked up by the model. And then once we start a KZ filter, what I'm doing between this top right and as we move down and around is filtering out cycles that are below a certain threshold that I can design. So in this top right one, I'm filtering out anything that's below about 3 days. So we're calling that synoptic. So this is anything that's going on and contributing to the wind speed cycles that is between about 3 days and about 3 weeks. And again, you can see they're missing the peaks and the troughs and missing some of the gust speeds. And this becomes really apparent as we travel from that subseasonal to seasonal area. So you can see that this MERA2 in the seasonal plot is broadly like higher than this example for, this is our seasonal bias station for the ISD. And so like the issues that happen at a subseasonal scale kind of bubble up, and you can see them easier as we move upwards through time. Still, again, in the decadal cycle, MERA2 broadly overestimates, and then there's this really interesting ISD trend here that I'll point out that I don't really have time to talk about here, but we do think that this is a real signal that you can read about. So a quick summary of part one is that we were able to quantify wind speed differences between the measurements and models. Those propagated to dust mass emission differences, and this is within the Descartes dust emission scheme. And then we were able to actually pin down why that was happening between the seasonal and subseasonal. And this can help the UFS even though it wasn't in the UFS. So this was in MERA2 and GEOS, but these mesoscale circulations are generally difficult to model, and especially these subgrid parameterizations. And either way, we need to include them in the UFS, either in GoCart or in the Fengsha dust emission scheme. And during all of this study, we found that we were really doing a sensitivity analysis of the wind speed, and we were finding that we were running up against things like the source function or the sediment supply map, whatever you want to call it, in your camp is what is on the ground that we know is contributing to the efficiency of dust mass emitted. So that's where we went for the second part. So before I get into it, everybody always asks me, Emily, what is an alluvial flow? What's an alluvial fan? So this is an alluvial fan on the left here. I actually took this picture. I got altitude sickness for this picture, so I'm very proud of it. I was actually at the UFS workshop 2 years ago now, and found out that there was this alluvial fan nearby in Rocky Mountain National Park. And so the Saturday after the workshop, I kind of sprinted up this mountain, which is how you get altitude sickness, it turns out. And I was able to get this beautiful picture of this alluvial fan in Rocky Mountain National Park. And you can see the scale of this, like trees are for scale here. It's actually not that big. So this would definitely be at a subgrid scale to any model, any system that you're running. On the flip side, on the right hand, these are also alluvial sediments, which are being blown off the coast of Namibia in this case. And so these are a lot bigger. They still could be subgrid scale depending on where you're working at, but you can see that this would be a difficult thing to actually model because it's got to span everything between 500 meters on up to several kilometers, and they're really narrow as well. So an alluvial is ultimately something that water has washed out all of these sediments and deposited them in a location where you can have that really efficient emission. So when I first started this, I wanted to learn how to run the UFS, and that's the first thing that I did was I did a baseline model run, and I wanted to look at AOD. Originally I was looking at this feature here off of the west coast of Africa, because if you remember your dates, this is actually the Godzilla dust storm that was forming off the coast of West Africa there. But as I was looking at even just one day, one model time step, I started noticing there were other things that were missing. So that's what this middle panel is. So I've blown up the southern part of Africa here. This is actually the coast of Namibia, and I've circled it because there's nothing there. This is AOD, and you think that there's nothing there, but then the MODIS overfly at the same time step, the same day, notices something, and you can see the blue-green highlighted here in the same circle. And spoiler, it's actually the same picture that we've been looking at. So like we know something is there and we're not seeing it in the model, and we think it's the alluvial flows and the alluvial sediments. So this really spawned two questions. The first one, can we better represent alluvials in the dust emission scheme? And two, can we use the source map to better understand our climate system? Because once we have identified globally where the alluvials are, where the dunes are, where these sediments are, we can start asking an absolute array of questions. How does it impact hurricane formation? How much of our emissions are coming from alluvials? How much are coming from dunes? How much are coming from large sand seas? The world is your oyster for questions after this. It's very exciting. So how do I make a map of the entire world and where all of these small alluvial features are? I need two data sets. The first one is hydrosheds, and this is a fantastic data set initiated by the World Wildlife Fund back in 2006, and it is super high resolution. You can get 90 meters at the equator, which is great. And this is well used. Everybody loves this hydrosheds data set, and it has this key reporting in it. It's the flow accumulation, and that's what we'll go on to use further down the road. And this is really just a measure of flux, really. It is all of the cubes on the planet are connected, and you can tell how much water is coming into a place with those alluvial sediments and how much is leaving. And so this data set allows you to see where the sediment due to water is accumulating at. And then once you have that, we can use MODIS RGB imagery, because then we need to know where the dry sediment is. So if we know where the water has transported something, we need to know how much of that is dry. So as the days go on, we use MODIS imagery, and we can do really the whole MODIS record at this point and tell you where these things match up. So how we do that is actually, there's this fantastic method using an HLS index. So this is the same RGB image that you've been looking at. It's just raw out of the MODIS camera. You can see the alluvial streamers here that we've been looking at. And if I were to hand you a marker and I said, please, on this image, would you try and circle where you think all of the sediments are? You could do it. You guys are smart people. And that's what we're doing here is we're transforming into a HLS, which is hue, lightness, and saturation, if you've ever done image processing. And we're extracting that H band because it's been shown that it's really efficient at identifying where the more red and yellow dust sediments are. So if you gave me back that picture, it would probably look a lot like this. And since MODIS is at 500 meters and our hydrosheds is also at 500 meters, we can put them together, but not before we do something called a min-max normalization. So we want them kind of relatively in the same scale so that RGB is a small value, or the HLS is a small value, but the flow accumulation is a huge number, absolutely huge. So we do a log base 100. This is an example. This isn't exactly where we were a moment ago. It just highlights a couple streams that look really pretty for these slides. And so we do a min-max normalization on them, and we can get that really pretty stream features popping out, and then we can quite simply intersect them because they're at the same resolution at this point. We can talk about resolution sometime else because there's a lot of work that went in between the MODIS resolution and what we can use in the model, which I don't have time to talk about here. So this is what pops out of that method. So we've put the MODIS RGB HLS on top of the hydrosheds, and what we get is called a preferential source map. These are just two examples of 2 days. The left one is in June and the right one is in January. And we started to notice that we could see the seasonality that we expected, which was really exciting. I've put this red bar in here to show you how the PSM changes in like the Sahel region throughout the year. And then this off the coast in June is that Godzilla dust storm again, which when this first popped out, I was like, oh no, it doesn't work. Like we're not doing something correctly. I'm not doing something correctly. This is actually really encouraging because this dust storm was so thick that you could see it from space, and this HLS index is sensitive enough to pick it up and say, yeah, that looks like alluvial sediments to me. You can see that from space. This is actually cleaned out in the final product that goes back into the UFS because the ocean is not a source of dust, it's a sink, but it was really exciting to see, and you can see how the structures change between summer and winter in this particular region. So zooming out a little bit, the left-hand figure is the SSM as it is currently in the UFS. So this is calculated using the albedo method. It's a fantastic source map. It does change seasonally already, which we're hoping to add to a little bit. So you can see the highlighted desert regions of like the Sahara, the Arabian Peninsula, and then on the right-hand side is our preferential source map. And this is for June 2020, just to show you an example. And this is what the albedo method could be potentially missing. So this is something that we're hoping to add on top of the current SSM. And you can see those sources in like the coast of Namibia that are much brighter than in the current albedo method map. Some things over Australia as well, and some highlighted areas through the Arabian Peninsula and through some of China as well. So just as a quick example, because I know I'm running low on time, is I've zoomed in so we can come full circle back to that coast of Namibia. The left-hand side is again what is in the UFS right now. And it does a fantastic job of highlighting all of these dust emissive sources. This is a salt flat lake, a very old dry lake bed, does a great job of highlighting that. And then this on the right-hand side is the preferential source map for the same month, and this is what we think it could be missing. You can see some of the river structures here. So this is like a dry riverbed, and this we were really excited about because this is actually a median of every day in June 2020, and so we were able to retain the structure there of these large alluvial features. So again, what we want to be able to do is ultimately add this back into the Fengsha dust emission scheme and be able to account for where all of the alluvial sediments are and see how much that affects our AOD. So currently we've seen that alluvial flows are not defined in the UFS, and we're able to actually make a map of them. And hopefully this will help us account for where on the planet's surface these emissions are coming from and improve the estimation of mass of dust emitted. So some key takeaways. Way back at the beginning, we talked about wind speed and source control and how they work together to estimate mass of dust emitted. The wind speed estimation needs improvement to better parameterize seasonal to subseasonal circulations. And then there's a whole nother episode about threshold wind speed we can talk about anytime. The preferential source maps can be improved with the addition of alluvial sediment identification and ultimately help the UFS further our understanding of where in the world dust comes from and how much of it there is. I'm going to leave this last slide up if that's okay, and just thank you so much for listening.
Thank you so much, Emily. We've got a minute or two for questions. I'm going to go over to the question document. Well, there's currently no questions at the moment.
I should mention that the Wings Fellowship was pretty instrumental to all of this. I wouldn't have been able to actually learn the UFS and try and fulfill my dream of becoming like a modeler without that. So it's been fantastic.